The assignment, all done?
Yep.
That's not a joke. Let me go over it briefly, and hopefully, at least, even if you get stuck, most of the code was provided to you. Okay, so if you take a look at our last assignment, I drew this picture over here so that hopefully we can easily see what we are doing, right? For example, as you know, we do a forward pass, right? So the forward pass, for example, we get an input of x, which is because we are doing those MNIST type of digits. So we get 28 by 28, and as you guys saw how we reshaped this using Python to make it 784 by 1, right? So that's the input if you take a look over here. So that's the 784 by 1 input. Feeding, then we multiply by the weights. So as we saw in the last lecture, it will be W1 times X1. So because this is 784 times 100, so remember the way we create the size of the weight matrix is it's always output, comma, input. So output is 100 neurons, input is 784, so the size of this would be, it should be
100, 784.
100 by 784. And then this is 784 by 1. And the bias, every neuron has a bias, so if we have 100 neurons, there will be 100 biases. So anyway, so this is our S1. So that's our sum. Then we pass it through the activation function, for example, sigmoid. So then we get A1. So A1 is whatever sigmoid of S1, right? Okay, so then we go to the second layer, and in the second layer, so as you can see, this A1 will be multiplied by, W2 comes first in the proper matrix multiplication. Okay, so this is now output neurons are 10, input is 100, so 10 by 100. Then, where did A1 go? A1 was 100 by 1. So this will be 10 by 1 plus B1, 10 by 1. So that will be S2, then we pass it to the sigmoid and compute the loss and so on. So the main concept that we have gone over a few times, and let me emphasize that, is the forward pass is easy, right? The backward propagation is where you have to be careful as we do back propagation, okay? So our goal is really to compute the gradients, meaning we have to compute gradient with respect to delta 1, gradient with respect to W2, gradient with B1, gradient with B2. So these are our model parameters, okay? Gradient with respect to W1 is basically partial L over partial W1, meaning start from the loss and go up to this W1 point, right? So if we write starting from here up to W1, as you can see, what will this be equal to? This will be partial L over partial A. So we go up to, A2, up to this A2. Then partial A2 over S2, right? Then we move up to this point. Then S2 over
A1.
S2 over A1. So we are up to here. Then let's go A1 to S1. Okay. Then finally S1 to W1. So partial S1 to W1, right? So how is S1 related to W1? S1 is W1 X1 plus B1. So what will this value be?
The input.
So it will be simply X1, whatever the previous input is, right? So now to make our things easier, this is where we come up with the concept of delta. Even though technically you don't need it, you can just go up to any point and write the whole chain of derivatives. But if we do it in terms of delta, right? So for example, what is this quantity over here?
Delta 2.
That's delta 2. Okay, so then once we have the delta 2, if we multiply by W2, so see, for example, let's go over here. Let's take a look at this part over here. Let's take a look at this part over here. What's the definition of S2? S2 is
W2 times A1.
W with respect to A1. S2 with respect to A1, right? So it is W2 times A1
Plus B2.
plus B2, right? So if we did partial with respect to A1, what will happen? So now focus on this part. Only W2 will be left. So this is really W2. Okay, so then what do we call further? If we go A1 over S1, this is the
Activation.
derivative of the activation, which is A1, 1 minus A1. Okay, so what do we call this whole thing? Delta 2 multiplied by W2 basically is giving us the derivative up to this point. Further, derivative of the activation function, isn't that
A1.
delta 1?
A1.
So this is basically, this whole thing from here to here is delta 1. Once we have the delta 1, then from delta 1, if we further take the partial derivative with respect to W1, which is really the input that is connecting to it, we'll get the gradient with respect to W1. Okay, so to summarize, okay, once again, the important concept was rather than computing a full chain of derivatives, compute delta 2, then compute delta 1 from this delta 2. How is delta 1 computed from delta 2? What do we do? What's taking us to delta 2?
The weight.
W2,
Times.
okay, which will give us the chain of derivatives up to this point, but there's another activation involved, right? So then further, A1, 1 minus A1, if you're using sigmoid, is how delta 1 will come out to be. Once we have the delta 1, then the W1, B1 can be computed from the delta 1, because then we further go see what the next derivative will be. So if we already know S1 is W1 X1 plus B1, right? So if I further multiply by partial S1 over partial W1, which will give me the gradient W1, which as you can see is simply, if I take the derivative with respect to W1, is simply X1, right? So gradient W1 becomes delta 1 X1. Okay. So in short, let me turn this off. Okay, let me just turn this on. Okay, so what I'd like you to remember is it doesn't matter how many layers we have. Let's say we went to somewhere over here, then this goes to over here. Okay, suppose, let me make it a neurons over here. Okay, so suppose this is some delta 4. Pretend we have 5 layers involved over here, right? And set of W4 takes us from this A3. So this is the third layer, delta 3. So delta 3, as we multiply by W4, meaning A3 times W4, this is B4, will, move us forward. So let's pretend we already knew delta 4. Okay, so the question is, what will be the gradient with respect to W4? Okay. Okay, so if we take a look at this S3, right? Oh, sorry, S4. S4 is what?
W4 times
A3 times W4
plus B4.
Plus B4. Okay, so to compute this gradient, what we have to do is we have to multiply delta 4 times partial S4 over partial W4. So if I did partial by W4, what will I get?
A3.
A3. So as we have discussed, the gradient for a weight is basically whatever the previous input is that's feeding to it. If it's A3, it's right. Or you can reason it out by writing it. Okay. Very similarly, can you tell me just by taking a look at this picture, what is gradient with respect to B4?
Simply delta 4.
Delta 4, exactly. Okay. How is delta 3 related to delta 4?
There will be delta 4 into the weight, that is W4 plus the activation function.
Plus there's an activation function involved over here, so whatever is the derivative of the activation function, right? Okay. Anyway, so today we'll use this concept. So a couple of new things that I'll show you today, which are very important, is let's take a look at our character recognition example, so the MNIST data. Okay, let's take a look at the architecture that we created. Was how many inputs?
784.
4 by 1. Then this basically went into how many neurons over here?
100.
100. Okay, then further, okay, we went into W2, and how many neurons over here?
10.
10 neurons. Okay, so let's say we feed in some unknown digit. Nobody knows what that is. Okay, let me make this a little bit bigger. So let me make the output neurons 10 neurons. Okay, suppose the outputs came out to be, let me make it 4 and then rest. Okay, suppose they came out to be 0.11, 0.23, 0.91, 0.41, and so on, 0.31. Okay, this is how the outputs came out. We gave it some unknown digit. After we've already trained it, based on the weights, we compute the output. This is how it came out. Okay, so what would we indicate? What digit is it? Let's pretend all of these values are less than 0.5.
Number 2.
So remember, this means digit 0, digit 1, digit 2. So it has to be digit 2, right? Okay, so if you do the assignment, okay, and if you, because remember on purpose, I did not want you to use all 60,000 images for training, even though you have those available. We only wanted to use 1,000 for training, right? Okay, so if you use the stochastic, last time we discussed there are 3 versions of the algorithm that you are implementing in your assignment. Stochastic gradient descent is one of them, correct? Then there's the batch gradient descent. And then there's the mini batch. So, okay, what's the difference between these three? Let me just briefly go over. Okay, remember our general training loop goes like this for I equal to 0 to num epochs. Okay, or j equal to 0 to num training data. Okay, so then we pick one of the training data, x of j, we feed it to our network, we do the back propagation, we adjust the gradient or adjust the weights and biases after we have computed the gradients. Okay, so if this is done inside each loop, meaning for every training data, we compute the gradients, we adjust the weights and biases after each run, then that's called the SGD algorithm, the stochastic gradient descent, right? Okay, alternatively, what we can do is, inside our inner loop, okay, we feed in one data, okay, we compute gradients based on this data. And we basically accumulate these, meaning before this, we set gradients to 0. So like np.zeros, you can create an array for the weight matrix, weight gradients, bias gradients, and so on, right? So you compute gradients, and then basically you do del W1 plus equal to whatever gradient you computed. So meaning you're updating it. Same thing, del W2 plus equal to del B1, del B2. Of course, in Python, rather than calling del, you may actually physically, we can't use this triangle symbol, so you'll have to call it, for example, del W1 as an example, right? So anyway, we update these. So the inner loop basically keeps updating those, okay? So then after this loop is done, meaning the whole, we've gone through all the 1,000 training data in our example, then outside over here, we will do W1 equal to W1 minus learning rate times, okay, the gradients that we have accumulated, divided by 1,000 or whatever the num training data is. So if it was 1,000, we'll divide by 1,000. Same thing we'll do to W2, same thing for B1, same thing for B2. So if we do this, meaning accumulate the gradients for all the training data, and at the very end, we update the weights and biases by taking the average of all the 1,000 of or however many we had in our training data. So this is really taking the average gradient, as you can see, to update the weights, right? So this technique is called the batch. So batch gradient descent. Okay, so first let's pause for a minute and see which one works better, okay?
The weight has to be still initialized to random in the mini batch. The batch gradient that you just discussed?
Yeah, the weights, see these are the gradients, not the weights. So the weights over here, again, minus 0.1 to 0.1, same thing for W2. So these are initialized randomly, okay? But before you start the epoch, you set all the gradients to 0, meaning delta W1, delta W2, B1, B2 are all set to 0, okay? And then because otherwise if you don't initialize them, who knows what was the last value in the previous epoch, then it will mess it up. So setting them to 0 before you start the epoch is very important, okay? And then at the end you update it, okay? So the question was which one will work better and why, okay? So, okay, of the two Not always, but generally the stochastic gradient descent works better. Okay. Why? Because, for example, let's say we have 1,000 training data. Okay. Let's say we have 100 epochs. So how many times, if we were using stochastic gradient descent, remember then this part will be inside this loop.
Yes.
Okay, so then this will go over here for the SGD. So how many times will be updating the weights and biases? 100,000 times,
Yep.
right? So even though it will fluctuate, so let's say this is our loss. Okay, as we keep improving the weights and biases, the loss will gradually go down, but it will go down something like this. Okay, because every sample that's getting, maybe it will make it worse, maybe it will make it better, but as we keep going, hopefully we'll keep making it better, but it will be quite a bit fluctuations in the loss, right? On the other hand, if you take a look over here, if we are doing the batch, at the very end, this is the average gradient of all the 1,000, right? So even if some gradients were very large, some were very small, what will it end up doing?
Average.
The average was, so this will be a little more, so this is the SGD behavior. Okay, the batch gradient descent will look like this. Okay, it will be very slow compared to this one. Okay, because we are only doing, for our example, how many times we'll be updating the weights and biases? 100 times. So for you, after 100, it may be basically somewhere over here, after 100 epochs. Okay, so you may have to run it like 1,000 epochs for it to do something meaningful, right? So the downside of the batch is takes a long time. Okay, another small downside is, in our case, our training data was pretty small, 1,000. But if we have 1,000,000 training data, each data was only 784 by 1. But what if our training data is like 100,000 by 1, and you have 1,000,000 of those? 1,000,000 times 100,000 is what we need the memory to be able to store it in our data structure. So the memory also becomes an issue in the batch, especially if the data set is large. Okay, so these days it's pretty much well accepted that this is the best approach because it will cause less. So this will behave more like, this. So there will be some fluctuation depending on the batch size. So for example, in the assignment, I had asked you to pick a batch size of
50.
Is that 50 what I asked?
Yes.
Okay. So with a batch size of 50, right? So now you'll see we'll have another K loop over here for K equal to 0 to whatever non-training data. Divided by 50. So if we had 1,000 training data, this loop will go 20 times. Okay. So basically, now before you start this loop, over here, you will set the gradients to 0 right here. Okay. All the del W1, W2, del B1, del B2 will be set to 0 right here. Okay. Then after you've gone through. Sorry, my mistake over here. Then for example, 50 times you'll do the accumulation. And then after 50 have been accumulated, then you will update the weights and biases. So if we were given 100 epochs, batch size of 50, how many total updates will we do over here? 2,000. 2,000. Okay. So you can see it's a compromise between the two. Okay, so to summarize, you will accumulate these for 50 of the training data. Okay, And then, so you can maybe put another loop over here for L equal to, let's say, 0 to 50. Okay. And move this over here. Okay, I'll give you a better pseudocode in the handout. Yeah.
Will that be x of k, because you're running through the k loop, right? So instead of j, that will we be iterating through k times the batch size?
Yeah. So basically, what you will do is you can use the slice operator in NumPy as an example. So you'll slice it from first time 0 through 50, second time through 50 through 100. So each time you'll slice the data and you'll run this loop 50 times, and you'll pick whatever you sliced on. Okay. And I'll put it in a slightly neater way in the handout and give it to you. So anyway, to summarize, in the mini batch, if the batch size is 50, you'll pick 50 of the training data randomly and compute the gradient, accumulate the gradients for all 50, and then you'll divide it by 50 right after you're done looping through all the 50. Okay. So that will give you a slightly more proper control over the training. Okay. So from now on, all your implementations, you'll be using mini batch. You'll be picking the batch size. What the batch size is, we'll decide as we go on for a given problem.
Question, when you set up, let's say, Delta 1, Delta 2, grads, do we have to first initialize them as like the size of those matrices? Or
Okay.
can we just actually just say Delta 1 equals, blah, blah?
In Python, if let's say you had already created an array, let's say 10 by 20. Let's say you had another B 20 by, let's say, 5 as an example, right? Okay, so if you did C equal to np dot A comma B, you don't have to declare C in advance. Automatically will make it 10 by 5. Okay, however, if you were doing something like this, C plus equal to, or C equal to, C plus np dot dot, either way. Okay, so then obviously you have to initialize it in advance to some zeros. Otherwise you can see it will not do the accumulation properly. So to short answer to your question, for the mini batch, you should initialize these arrays for the gradients and set them to zeros. Using np.zeros would be an easy way to do it.
And how about in just regular SGD, we have to initialize it?
No, because then all we're doing is creating the gradient just for one case. It will automatically create the variable for you as soon as you assign it. Okay, so in pseudocode form, just to summarize, our mini batch SGD will look something like this for I equal to 0 to num epochs, for J equal to 0 to num training data divided by batch size. Okay, so again in our example, if this is 1000, batch size is 50, this will go 20 times, right? Then you will have for k equal to 0 to batch size. Okay. Pick batch size, number of training data. And before you do this, over here is where we will initialize delta W1, delta W2, delta V1, delta V2, two zeros. Okay, so then, so in, I don't really need to do this. Okay, because I'm going 0 to batch size. Okay, pick training data. Okay, from current batch. So the first time your batch will be 0 through 50 as an example, then 50 through 100, then 100 through 150, and so on. So pick a training data from the current batch. Now you will do delta W1 equal to delta W1 plus, so whatever was the or let me just say plus equal to delta W1 plus whatever the gradient was. So I want to be there plus. Okay. Same thing you will do W2, B1, B2, and then after the K loop. So after K loop, then you will do delta W1 equal to delta W1 minus learning rate sorry, W1 equal to times delta W1 divided by
The batch size.
batch size. So anyway, this is how, and same thing for W2 and so on. So your mini batch algorithm will look something like this in pseudocode form. Okay. So hopefully you guys will be able to go and put it in your current assignment. Yeah.
So I'm confused because the gradient descending, descend, if you have 1,000 images and 100 epochs, you're gonna do 10,000 outputs, right?
If you have 1,000 images and 100 epochs, you will do 100,000 updates in the stochastic gradient descent.
So then on the mini batch, if I have 100 epochs, 1,000 images as well, but then my batch is size 10,